I'll talk about relational learning, covariance information. These are the people I work with throughout some of the things that we talk about. And just to give an idea of what this talk will focus about, before we saw how covariance information can be used to estimate graphs, here we are instead assuming, again, we have data from different fields, we have observations, right? And we know that these data are somehow interlaced, there are some interactions among different points and so on. And we want to capture these kind of interactions through a covariance matrix. And then we want to say, what if we use this covariance matrix for machine learning or for signal processing with the covariance? What can we say about the signal processing or the machine learning model that we can apply on this covariance matrix? So again, we can think of rain data, the same picture appeared already today. So yeah, we have recording in different areas of the rain, and then we want to somehow process these recordings by taking into account how different areas of the brain might activate for the same action or for the same behavior of a person. And then, yes, similar things on financial networks. We have that maybe similar stocks might vary their price in an analogous way, or if a person wears sensors on their body and then they move, then the movements of different parts of the body can be coordinated, right? So we might want to exploit these kind of coordinations to process this data and then to ultimately solve a task in the end. And to give an example of a very popular technique that relies on the covariance matrix, since we are dealing with covariance matrices in the first place, PCA. So PCA takes data sample X and then takes a covariance matrix of the data, which is you assume to have a true covariance that generates this data. And then you take the eigendecomposition of this covariance matrix, and then you project your data sample into the eigenvectors of this covariance matrix. And this projects the data into a space where each direction maximizes the variance of the data, right? And you order, so you can also do dimensionality reduction by just taking one or two main directions, and that will preserve as most variance as possible. Other things you might do with the covariance matrix is topology inference. We saw something before where you're looking at the covariance of the data and you want to exploit that information to learn a graph. And then once you have the graph, you can use it for downstream string processing. So this approaches, there are many approaches in the literature that do this in two steps, right? So you first estimate the graph, and then you use it for whatever you want to do next. However, every time we use a covariance matrix in practice, we always encounter this finite data effect. So we know, we assume there is a true covariance that our data is drawn from. But in practice, we never know the true covariance, but we only know the empirical covariance, which is estimated from the number of samples, from the samples that we see. And in some cases, right, so if I don't have enough samples, or if my samples are very large dimensional, my estimate can be bad. So just visually here, the empirical covariance contains a lot of noise, right? So, and in practice, we will always need to work with this, right? So how do we deal with that? And this creates more problems, even if we want to do PCA, right? So here I have a very simple simulation where I have a true principal component, that's this one, and then I generate a few samples, and then I compute the principal component from the samples, and it's this red line, right? So it's very, very much off, but in practice, that's what we work on. So how do we deal with this when we want to do machine learning? So this is the problem setting that we will try to investigate today. We want to exploit covariances to process data because we assume that covariances contain useful information. But we want to do it in a stable way because we want to somehow deal with this kind of behaviors where we need to estimate covariance. It's not exactly the same as the true one. We want to do it efficiently. And we want to tackle a variety of settings that we will briefly touch upon. So some static data, we want to use temporary data, and we will also account the situation in which there might be some bias in the data. So not all groups might be equally represented. So this is the outline, and I'll start by introducing how we process data through their covariances. And the answer is quite simple. We build a graph based on this covariance, right? So we have a data sample X, which contains n features, and now we see each of these features as a node, and then our signal on each node will be the feature, corresponding value of the feature. And then we build the graph where the edges are the covariance values among these two different features. And then we do filtering over the structure. So how do we do filtering? With the standard graph convolutional filter approach that we showed introduced before, so I don't need to go through the details here. But it's the same, right? So instead of the as shift operator, we use a covariance matrix in this case, and then we can build a neural network based on this filter. So we basically plug this filter into a nonlinear activation function, and then we have multiple of them in parallel. This is a layer, and then we can have multiple layers. So this architecture can do deep learning, and it can process, can increase its expressivity via this nonlinearity and via these filter banks that allow to have multiple feature sizes. Now, what's the main advantage of doing this? The advantage is that we can have a bound that looks like this. So we have our filter applied on the sample covariance, the one that we actually observe from the data, and the same filter applied on the true covariance, which we don't know. And we can find a bound for this distance, which tells you, ideally you want to work here, but you will never be here. So in practice, you work here. How far away are you from the ideal case where you want to be, right? And this bound has two terms, right? It depends on the number of samples, of course, because the more samples I observe, the better estimate of the covariance I have, and then this bound will go to 0 for infinite samples. And on the data dimensions, I mentioned before that larger samples mean it's harder to estimate the covariance, right? So if the samples are larger, then my bound will be larger as well. And something else that depends on the data distribution that doesn't really matter now. So nice, we can have a graph neural network on the covariance matrix and be stable, right? So that's already a very nice result. But we still have a few problems to solve. The first one is that this estimator, so if you just compute a covariance matrix from the samples using the sample covariance estimator, you might have a bad estimate in some settings, right? So if your true covariance is sparse, which of course you don't know for sure, but you can assume based on your data, then the sample covariance estimator will be worse than other alternatives. Plus, it's computationally inefficient because you have this n squared matrix, and in this case, right, you have only a few non-zero values, but you will have a lot of non-zero values here, all of them because of noise, because you are estimating a noise matrix, right? So let's start with these two challenges, and let's look into sparse matrices, sparse covariances for neural networks. So here what we do is we investigate the framework I introduced before, these covariance neural networks, when we have a sparse covariance inside. And the way we have a sparse covariance is by thresholding, where we either hard threshold, so set a threshold and remove everything that's below. We soft threshold, so we set threshold, remove it from all the values, and remove everything that goes below 0. And we also consider stochastic specification, where we don't need to choose a threshold, but we just drop covariance values stochastically based on some probabilities that we defined. And again, we want to find a bound for this kind of architecture that looks like before. So same as before, but here instead of just the sample covariance, I have the thresholded sample covariance, right? In this case, it's hard thresholding, and main takeaway of this slide is that we can compute the bound, right? And we have also the number of non-zero elements in the true covariance in the bound, which means that based on how sparse it is, this bound can be particularly small. And we can do the same for the soft thresholding technique, where we have something that's even tighter. So this value is even smaller than what I had before. And finally, we can do this also for stochastic specification, but now in this case, we have two terms, right? Because in this case, we're just dropping edges stochastically. So we have one term that depends on how well we are estimating the covariance. So this is the same that I've discussed so far. We have something that tells you, okay, you only have t samples, your estimation will be as good as it can be given these t samples. But then we have another term that depends on the sparsification. So let's say I have a covariance matrix, I want to make it sparse because I want computation to improve. But then I will lose information because I'm making it sparse. So this term tells you how your sparsification level affects your stability of the model, right? And of course, more sparsification, lower stability, but computational efficiency and vice versa. And just quickly some results on some data sets. I'm comparing the cross here is the standard covariance neural network, and all the other points here are thresholded or stochastic VNs, where I'm changing the sparsification level and running the same task, and I have time here, accuracy here. So basically, what happens in all these cases is that, of course, time decreases because the models are faster, and in all the cases, there is this one model where accuracy also increases. So here, intuition can be that your sample covariance that you estimate from the data is already noisy. Like, this is real data. We don't know the true covariance, right? So even if we impose sparsification, doesn't mean that sparsifying reduces accuracy, it improves, because actually the true covariance is probably sparse, and then we are not estimating a really sparse one because of some noise in the data. So these kind of estimators can also help accuracy, not only performance, in terms of efficiency.
So accuracy high is good or bad?
High is good.
Okay. Because you said at least one is better, but all of them are, I mean, many are better.
Yeah,
At least one is better, has better accuracy, you say, but
That's one.
So if you try
yeah,
out,
but there's many that have.
yeah, maybe at least one.
Yeah. So,
So this kind of solves two problems. So can we have an estimator that works well in case our true covariance is sparse, and can we make the model more efficient? We still want to deal with two more settings, which I will just briefly touch upon. One is, what if our data is temporal? We've discussed dynamic graphs before. And what if we have some bias in the data? So let's start from the temporal one. And so these are basically, two of the applications I talked about before. And I didn't mention it, but they are actually temporal data, right? So brain data, I have recordings of the brain over time. And of course, the temporal sequence in which I observe this data matters for processing. So I can process it with a model that's completely unaware of time, but this will lose some information. So I want to introduce this time awareness. Same holds for financial or traffic networks. And the way we do this is by building a spatial temporal covariance neural network, where basically we have time series, and then we take snapshots of this time series, right? And each snapshot, we build the covariance matrix, right? So we will have a string of covariances, kind of. And then we process each snapshot separately with this VNN, but then we also process the time, right? So we have this temporal window, we process these snapshots, and then we have coefficients that aggregate these snapshots together. So we have a spatial term and a temporal term. And this creates our representations, which will be used later for learning, can be forecasting, can be anything else. And now what I have done is only, covariance is only one time size, but then we are looking with the times. What happens if my covariance is also across time, right? So I might have that the temperature in Delft is affected by the temperature that was in, I don't know, Amsterdam 3 hours before, right? So looking at these cross correlations across time and across space as well, which of course makes everything more powerful, but also everything more complicated. So let's see. And finally, last setting is what happens if I have bias in the data. And then bias in the data, oh yeah, I didn't mention, but we can also compute stability bounds before and everything. Just trust me. I mean, there's the paper, you can look at the paper also. What we want to do here instead is we have some bias in the data, right? So what happens is that we have, simple example, two groups, right, of data points. The blue group has a lot of data points, the red group doesn't have a lot. And then we want to do PCA, right? So we have one principal component for the blue group and one principal component for the red group. And now if you just do PCA of the whole data set together, given this unbalanced representation, then the principal component will be strongly affected by the blue line, because that's the majority group, so it will have a large contribution on the overall result. But now we want to make it fair, right? So what we do, we look into the literature for fair principal component analysis, and one way to do it is you compute these two principal components separately for each group, and then you take the average, where the average doesn't depend on the number of samples of each group, right? So you get the green line. And this, you can say, it's a fair estimate of the covariance of the principal component for both groups. But this is not the end of the story, because what happens here is that we have a small number of samples, right? So we are still working with finite data. And so the blue group has more samples, so we will be able to have a good estimate of this principal component. But the red group has fewer samples, so we are not able to estimate the red component as well as the blue one. So overall, even the fair PCA will give this result, which is more leaning towards the blue component, because that's what we are better at estimating, right? So we want to somehow deal with this case where the stability, well, the instability in computing the covariance leads to unfairness. And so we do this by defining fair covariance neural networks, which somehow we show that the stability that I've discussed so far translates into fairness in this case. Because if I have a model that is stable to this kind of errors, then it will also be fair. So if I want to do fair PCA here, then I will basically bound the distance of the model operating on these two different components, right? So it will be able to improve fairness in that sense. Plus, VNNs are neural networks, so we can add a fair regularization term when we train them. And then we can do this end-to-end, so also the coefficients of the neural network can be trained to improve fairness on the data. And then we show, again, this is stable. And in practice, we can have this trade-off between how much fairness we want versus how much accuracy on downstream tasks we want. So this is, this was just to wrap up. So now we discussed how to exploit covariance information for learning. And in particular, we want to capture the hidden relations, unknown relations among the data points using covariance matrix. And we want to do so in a way that solves the instability problem that's intrinsic in covariance estimation. Plus, we want to be efficient. And we want to deal with a variety of settings where we want the data to might be temporal, the data might be biased. And we analyzed more or less all these challenges. So first of all, we defined covariance neural networks in a way that as a tool that processes covariance in a stable way. We extended them to a sparse framework where we have sparse covariance estimators, where we can still show the same stability bounds or even prove that even tighter, and we get better covariance estimates if the true covariance is sparse, plus it's more efficient. We defined the spatial-temporal VNNs for spatial-temporal data, so we want to count streaming data, so temporal sequences. We can also extend this to non-stationary settings, so if my data distribution changes over time, I can adapt, I can keep training my neural network to learn from the new data. And then we dealt with data imbalance and biased data in general with fair VNNs, where we can trade off accuracy and fairness via different strategies. So yeah, that's the end of the presentation. And if you have any questions, happy to answer.